Today we'll have the quiz, and it will cover probability and conditional. And prior to that, I'm going to quickly go through a little review of the code that we used and are using. As I've said before, there's commonality between Lab 5 and 6, so they're building on each other, but also highly related. So we're going to work from that perspective. And so this quick review will help you as you go forward with Lab 6, but also could be very helpful as you prep for the quiz. So listen carefully as we go through because, again, the quiz may echo some of the things we talk about. Lab 6 will be due next Tuesday, again, Tuesday night. So hopefully this afternoon you'll have a chance to dig into that and make some headway. Okay, so one note is there is on the YouTube channel a great video, very helpful, about 10 minutes long in terms of Lab 6. So I definitely encourage you to go to the YouTube channel and look to this video. One very quick note, the Nobel Prize was awarded in chemistry, and this Nobel Prize is particularly relevant to what we're thinking of, both as scientists, but also the sort of data science basis of the method is used to go from the sequence encoded in DNA for a variety of proteins to actually seeing what the three-dimensional structure of those proteins are, just like these kids are playing. Here we're not really playing. This AlphaFold 2, for which the Nobel laureates were awarded the Nobel Prize, is very unique in the approach it takes to the problem. It's a big, big problem, but also in the way in which distributed computing was used and continues to be used to solve this problem. So it is possible to kind of be a part of the project. So that's something cool to look for. And here I'll just note, in keeping with our earlier work, we can see this is over the last week. I captured this a day or so ago. We can see these spikes in the Nobel Prize, and this is the Google Trend data. So here what we see is search for Nobel Prize peaked during the announcement of the three. This is the medicine prize, closely related to biology, of course, chemistry, or physics and chemistry. Physics, as I mentioned in class, was closely related to machine learning, and some very nice algorithms there were developed and applied to some important physics problems. And now in our case, what I just reviewed, this is where the chemistry prize was awarded. And their approach isn't precisely machine learning, although related. So the spike in machine learning is not as great. And then the last thing I'll point out is the blue is the microRNA, which was connected with the prize in medicine and also formative in terms of ideas like the basis of some of the COVID vaccines. Okay, so digging into some little bit more helpful stuff, it's pizza time, okay? And with pizza time, we want to sort of review and refresh our memory as to how this code could be implemented in the best case. Now we're getting to the point where we have a number of choices in terms of how to execute the code. So here, with this function, we have the opportunity to take advantage of the conditional expression. So that's a requirement for defining this function. So here pizza is passed to the function as an argument, and then we make these comparisons. So here, if this is true, then this statement executes. Once that executes, then we go down and return the price, which has been defined here. If this is false, then the elif is executed. It checks if it's artichoke. If not, continues down, it'll check if it's pepperoni. If that's not the case, then the else, now this wasn't required in Lab 5, but many have this, the else is sort of the backup. It means or else. So if your pizza is none of these, it will come down to 11 as the price. and the price will be returned. So here with this piece here, what we're going to get is a randomly selected pizza, and we find out it's cheese. And then when we put the cheese in here, we get 10. So this works appropriately. Okay, we left off with the possibility, this function, pizza price, when we put in a particular pizza type, which could be one of these, typically a string here, it will make each of these comparisons. If this is true, it goes here, produces 10, and we have the else. And this will return 11 for any pizza that is not included here. And you can see Supreme is not, nor is Veggie. Okay, so they will return the default price. Then we can see what happens here. So now if we apply this function going forward, we can apply this function. And in applying the function, here I've put this in a loop. So this is going through an iteration. Here the in takes each of the randomly selected pizzas. Now here we're going to go between the pizza choices. So those pizza choices were given up here, okay? And this 5 is like an optional parameter. That 5 indicates that we are going to select randomly 5 pizzas from the choices available. And so this is going to generate an array of 5 different pizzas. The in is going to sequentially select each of those 5 pizzas, and they are going to be stored in the value pizza because of this 4. The colon indicates that then each time a pizza is selected, it's going to go through this loop. So the first time it's going to give us the price, it's going to be the cost. The money, which we initialized or started at 0, will now continue to add up based on each pizza and its cost. And we're going to count the number of pizzas. Then we're going to use this kind of nice print statement. So this is, kind of beyond the regular. This is an F print, which is a formatted print, where we put this F before. And then here you can see the variable count, which is counting up. And then pizza, which is the name of the pizza that was randomly selected. And then costs. Here I've even put a $ here. And then I've also added the fancy formatting here that gives us 2 decimal places for the floating point number that is reflected in the cost. Okay. And then at the end, we're going to sort of sum up what happened. So you can see here what happened. Pizza 1 was cheese, cost $10. 2, pepperoni, 15. 3, pepperoni, 15. 4, supreme, 11. 5, pepperoni. So see these pepperoni, it's coming in here, costs 15. Then this is the number, see count kept adding up. That's this plus equal. So now we're up to 5 pizzas, and they sold for a total of $66. So this is a kind of alternate way of doing was included in Lab 5, but will also be focused on in the quiz. So good to look at this example. Okay, 2 further things to look at before we get into the quiz. The first of which is simply this concept. We looked at this a little bit in terms of class on Tuesday. So here we're reading in this acid base. We get each of these words, okay? How do we get each word? Because we read this into a string, and then this split breaks them at the space between. So here we get a collection of words in an array. That's what these words are. Then here we can use an iterator, just like I said, the acid words, here they are, that's a list. So the in first goes to in, ironically, and that becomes word. And then that word is lowercased. And then if the word is acid, we add 1. If the word is base, we add 1. This is much like when we're counting the birds in in Darwin's book. So this is essentially what we're doing. And here in this case, we get 5 mentions of the word acid. And we also looked at a different way using dictionaries to count these words, but that was a case where we didn't just count one word or 2 words, acid or base, but we actually count every single word. And this will be in the end of Lab 6. You'll see this sort of very special code, which allows us to actually count the number of each. Okay, last little bit to review before our quiz. Okay, so here we have this simulation. This simulation is the random outcomes for computer-based groundhogs, but the computer-based groundhogs have no insight. In other words, they don't feel the weather or anything of these other sorts. So they're totally random. So this is the distribution of outcomes randomly for 530 in computer hogs. The red dot represents the outcome for our collection of 530 hogs. You can see there's not much distinction between the random outcomes and the special sense that our friend here has. So we might begin to wonder if there is much predictive capability there. So we're going to look at that very quickly. One way to look at it is by using the p-value. So can think of it, the prediction accuracy, that's from the percent correct, okay? But percent correct, for instance, if we get 50%, only half of the time is the groundhog correct. So 50%, we could easily sort of say, okay, around Groundhog Day, we could decide, toss a coin and say, I think spring's early, or I think it's late, rather than going through all the drama of bringing the groundhog out and seeing the shadow or not, these kinds of things. So the p-value is showing that 33% of the time, the groundhog does no better than random, okay? We typically look for 5% as a good barrier, a good measure there. Here, if we look at SXED, SXED does quite a bit better. Now, there's a caveat, only 9 measurements that SXED has recorded in our data set, but SXED is about 77% correct, so it's quite good. And here we can see that this red dot is not totally removed from the random outcomes, but there are very few of the random outcomes that do better than SXED, represented by the fact the bars are fairly short. So not many of those outcomes are better than SXED. In fact, only 3%. So if we look at Punxsutawney Phil, we see that Punxsutawney Phil also does not do very well. SXED, something special perhaps. So let's sum this up. P-value interpretation, 36% of the time, Punxsutawney Phil's prediction is no better than random chance, okay? Might say, okay, well, you know, it's a decent amount of time, 64% he does better than chance, but that's not actually very good, okay? In fact, in science, we would say, or statistics, we'd say, unless it is only 5% or 95% of the time, the prediction would be better than random chance, then we would start to say that there is a real phenomena surrounding Punxsutawney Phil. So there might be a lot of hype around Punxsutawney Phil, but in terms of a phenomena that we could discuss from a scientific perspective, there isn't support for that in the data set, unless this number goes down to 5%. Now, SXED is a very different story, 3%. So we would say statistically, SXED is a good predictor. At least the data supports that idea. Better than chance 95% of the time. Again, the caveat is only 9 predictions here. Okay, so now we're ready to do the quiz. The quiz is through Canvas. Should be fairly straightforward. You'll have 20 minutes to do it. And remember, 2 of the quizzes are dropped. So good luck with it. And afterwards, you're fine to stay around and work through your problems. The course assistant will be available to help. You can email me, but unfortunately, I'm not able to attend today's session. But glad to talk with you by email, or we can set up an appointment. Have a great day. Good luck with the quiz. Okay. Good luck.